now we get to something a little bit different, maybe a little hard. So now we're going to do the inside. I'm going to get a pen here. We're going to do the inside. So anytime you have inside of a conductor, you're happy, because E is 0. Boom, done, easy bist. If you got to go inside something that's an insulator, like this plastic rod, you're going to need to think a little bit more carefully about that charge distribution, okay? So here, this is still cylindrical symmetry, and we're going to use a cylinder. So I'll just tell you, the fact that I called that lambda, a lot of times when you do this problem, they give you rho, right? Rho is the volumetric charge density. And a lot of times it's easier to think like about rho versus lambda. But they do have a relationship. So I'm just going to throw that down here. Before I get too far, big picture here is that when we do Gauss's law, in general, there's only two hard things that you have to do every time you do a Gauss's law problem. The first, once you figure out the symmetry, then you're good, and then you need to remember what the area of the appropriate surfaces that you're dealing with. And then to calculate the enclosed charge in a surface often requires this kind of thing that we're about to discuss. Okay, which has to do with charge densities. So the question on the table is, if we have a lambda, but I actually kind of want to work in rho, let's see if I can find a relationship. So rho is charge over volume, right? We are going to be dealing with cylinders. So the volume is pi r squared L. And Q, by the way, I'm going to write R, like a big R, because that's the radius of our cylinder, okay? And so I'm going to notice that Q over L is lambda, okay? So I can write rho is lambda over pi r squared, okay? So that's going to be useful. Basically, rho is proportional to lambda, and then there's just a factor of that area of the cross-section of the cylinder. Okay, so we're going to kind of hold that in our back pocket, all right? So let's start again. Okay, so we're ready to draw our Gaussian surface. So we are looking, remembering, what does that electric field look like? That electric field looks like this, right? Radially outward everywhere. And so when we draw our Gaussian surface, we want it to be inside, because that's where we're looking for the electric field. And we're looking at the different parts. The only part, right, the end caps won't have any flux. So the only part that will have flux through it is this cylindrical shell, okay? So when we do E dot dA is Planck over epsilon naught, the E comes out, and then the area of the cylindrical shell is 2 pi r. You know what? Let's call this H, because a lot of times we use our capital L to mean the length of the full rod, and so sometimes it's easier just in our Gaussian surfaces to just call that H. during all these calculations, whatever size Gaussian surface we choose, those dimensions always cancel out. So, so you don't worry about it too much, but you do need to define it just so that you are consistent. Okay, so now we get to the fun part, which is Quincke. So we're thinking, how much charge is in that, okay? And Quincke is going to be rho times Venk, if you will, right? And again, the enclosed volume, that is the volume of our Gaussian surface. So that's going to be rho pi r squared h, where r, of course, is the radius of our Gaussian surface, because that's where we're trying to figure out what the value of the electric field is. So that's that r, our variable, and that h is again that that longer dimension of the cylindrical shell. Okay, so let's plug that in up here. Pi r squared h times a rho. Cool, cool. So many things are going to cancel here. Very interesting. What we end up with is rho over 2 epsilon naught times r. Okay, that looks pretty nice, actually. Just because we need to make sure that we stay in the problem, remember that rho up here is equal to lambda over pi r squared, and then we've got a 2, and we've got an epsilon naught here. Okay. Oh my gosh, times r. So this is important because this says that E is proportional to R. So as you start in this cylinder, the electric field at the center is 0. And it gets bigger and bigger and bigger as you get further and further and further. And if you look back at our other value for electric field, so actually let's look at how the outside and the inside compare. So this is the value lambda over 2 pi epsilon naught r that we got from the last video. And so that means that here is the radius of the rod, and it fell off as 1 over r. And at the inside, it looks like it's linear, right? It starts at 0 and it's linear. And then I want to stop before I just randomly join them. Let's actually see if there's a discontinuity or something. What is it? What is it at that surface? Well, E inside value gives you 2 pi epsilon naught capital R, and E outside gives you lambda over 2 pi epsilon naught capital R squared times R. So, yep, they have the same value. So that value is 2 pi epsilon naught R. So that is our graph of E versus R for a plastic long rod. So we're going to look a lot at these kinds of graphs of how the electric field varies as a distance from the center. I want to mention one more thing while we're here. You can, instead of deriving this rho is lambda over pi r squared, you can just do actually a general proportionality argument. And this one is probably more useful than the other one. So that's why I wanted to show you. Okay, so this proportionality argument is very, very useful. Remember, this is only for what's it called? Density. So when we solve for Planck, it's a ratio of the volumes times the total. So if we're thinking about, okay, so we've got our cylinders. This is the full thing. If you want to call the full rod length L, and then our Gaussian surface had an H. So if we're looking at the enclosed, so this, by the way, that has a radius little r, that has a radius big R. So our enclosed volume is pi little r squared h, and our big volume is pi big R squared L. And then the total charge of the whole thing is going to be that linear density lambda times the full length L. So what we get for our Planck is the L's cancel, the pi's cancel, and so we get lambda r squared h over big R squared. So that ratio of squares is a really common thing that you'll see. When we have cylinders, the ratio of volumes is going to give you a ratio of the radii squared. When we do spheres, and we're going to do this shortly, that ratio is 4/3 pi little r cubed divided by 4/3 pi big R cubed. So here, our ratio, you'll see that being cubed. So that's useful and important. But just back to the original question, just to make sure that this different way of looking at it was just a ratio of the volumes really works. We had E times that area, 2 pi RH, and then our Planck, which is right above us, lambda, little r squared h. There was an epsilon naught down here, can't forget that. And here we are, lots of things cancel, but what do we get? We get, so the h doesn't matter, as I claimed earlier, that that dimension of our Gaussian surface, it always cancels out. And we get down here 2 pi epsilon naught big R squared times R. So that was the result that we got before inside.